This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Are you a software engineer, developer, consultant, architect, manager? No matter what your role is, we want to hear from you. Please take a minute to complete our listener survey to help us make SE Radio even more relevant to you. Just go to se-radio.net/survey2023 to share it with us. That's se-radio.net/survey2023. Thanks for your support of the show.
Hi, this is Philip Winston for Software Engineering Radio. Today, my guest is Lukas Fittl. Lukas is the founder and CEO of pganalyze. He has worked as a software engineer in the Postgres ecosystem for the last 15 years, including as a founding engineer at the startup Citus Data, which was acquired by Microsoft in 2019. Prior to that, he was an early engineer at Product Hunt, which was acquired by AngelList in 2016. Postgres is one of the most popular database systems in the world with over 30 years of active development. Today, we'll discuss Postgres database performance along with the pganalyze tools. We'll start by introducing Postgres and pganalyze, and then tour through various Postgres performance-related features such as indexing, queries, scaling, maintenance, and if we have time, stored procedures. Welcome to the show, Lukas. And can you tell us what is Postgres in your point of view?
Of course, and thank you, Philip, for having me. So Postgres in general is, if you're an application engineer, you might think of Postgres as the thing that just does work behind the scenes for you. So Postgres is a relational database system. It's just turned 27 years old. So it's, old enough to drive a car and to write its own thesis. And Postgres was started at the University of Berkeley 27 years ago. And it is extremely popular today, right? So most likely, if you're using an application today, Postgres will be the backing data store behind it. The main data in the database is going to be stored in Postgres in many cases. And so really, to me, Postgres, is one of the most important open source technologies today.
What types of applications does Postgres excel at? I know it's a very general purpose database, but if there is an area of what it's most known for?
Sure. And I think there isn't necessarily one type of data that you can store in Postgres. I think generally what I've seen is that for system of record type data, right? So let's say you build an application and you're thinking, where can I actually store the data for my application? That's where Postgres excels at. But what Postgres is also good at is being extensible. So for example, PostGIS is a very popular extension for Postgres that allows you to work with geospatial data in Postgres. More recently, there's an extension called pgvector, which lets you store vector data in Postgres so you can work with your AI, ML embedding type data with Postgres. And so that's really the power of Postgres, is that flexibility of being able to support individual data types that are useful for particular use cases.
Yeah, I'm glad you mentioned PostGIS. That was going to be one of my questions. I think when we get into the specifics, we might come back to PostGIS and how it impacts indexes and other things. How about the cloud computing angle on Postgres? I know Amazon has this RDS service, and Aurora is a type of database. Are these Postgres under the hood, or are they compatible with Postgres?
Yeah, and it's a good question. So, generally you could run Postgres yourself on a virtual machine, right? So I think what I would always emphasize, similar to the Linux kernel, you can just run Linux yourself, right? You can build it yourself. But what's interesting, of course, is that roughly, I would say 15 years ago, database as a service kind of took off as a concept. And so I would say one of the most prominent early starters in that space was Heroku Postgres. Heroku these days, unfortunately, not that many people are using it anymore, but it, I think, was one of the first places that really brought developer experience as the main thing that they cared about in the experience. And so Heroku Postgres was a managed database service where instead of you having to run your own virtual machine, you were actually able to kind of have just a API that you could use. API in this case meaning, you run your SQL queries against a connection string. And so nowadays, of course, AWS and Amazon RDS service, as well as Amazon Aurora, is probably the most popular Postgres as a service database, managed database that you could find. What's notable there, I would say, is that Aurora, for example, is a fork of Postgres. So what they've done essentially is they've, taken the open source Postgres code, which is BSD licensed, so like very liberally licensed. And so they took that code and they essentially made modifications to the storage engine. And part of the motivation there was to increase resiliency. So when you have, different availability zones in AWS, they wanted to have a better concept of how the kind of resilient architecture of the database works. And so Aurora is essentially very tied to AWS's approach of doing things, versus RDS is it's still a forked version, but it's less, much less patched essentially than Aurora. And so if you want to be portable, right, if you want to have your Postgres work similarly on GCP, on AWS, on Azure, then it's certainly better to, in my opinion, focus on, the RDS type service. Or in Google, for example, you have Google's AlloyDB service, which is again their forked version of Postgres. And they also have Cloud SQL, which is their more standard Postgres. And so I think oftentimes it's actually better to not stray too much into the forks of Postgres, because you get kind of special behaviors that are unique to each provider's infrastructure.
This might be self-evident, but why is database performance so important?
Sure. And I would say, it kind of comes back to the Postgres being your source of truth, your system of record, meaning that a lot of cases when your application wants to answer a web request, for example, right, it will have to ask a database, and will have to ask a database like Postgres. And so one thing I saw this morning, for example, is so Google announced a new kind of mode of measuring page performance, right? So they're now saying, I think anything that's slower than 200 milliseconds on, a mobile device is actually a slow page, and they will rank it less. Now, you could think if that was an application, right? So if you were actually like querying customer data, for example, ultimately what you would have is a web request that goes to a Postgres database, and that request is a query, right? And so the query, if that is slower than 200 milliseconds, you would by definition fail that, kind of performance test. And so database performance matters because ultimately it is actual web performance, right? It's actually end user performance in many cases. And so whether it is measurements that Google makes, whether it is, actual end users being frustrated because your application is slow, database performance matters because it essentially builds a better experience for your end users of your applications.
And we'll get into this later, but certainly your ability to scale might be hampered by your database performance. So things are working fine when you have 10,000 users, but then you have 1 million users and performance falls apart. So I think that's something we'll discuss in a little bit. But I wanted to mention from a previous show that I'll cite soon, SQL is a declarative language. What are the implications for this as far as performance? It seems like it's related to the fact that you can't necessarily see what steps or instruct the database in what steps to take. You have to just count on it figuring that out.
Yeah, I think that's a great question. So I think you're essentially stating what you want, right? You're telling the database, please give me this data from this table and filter it in this way, or order it, sort it in this way. But you're not necessarily telling it how to do that. And so it is both, I think, the power of the database, but also, of course, the downside, which is the database will make that choice for you, right? So you can declare your intent, and the database will find a way to answer that query, to answer that intent of yours that you declared using the query language. Now, of course, this relates to index usage, right, and all these other topics. But I think really it is a fundamental nature of how databases work, especially relational databases work, is that you're not just saying, I'm calling this method, which works exactly this way, but instead you're saying, I want this data and I want it filtered and grouped and sorted this way, figure it out for me.
So let's start talking about pganalyze. When did you start working on this project, and what was the original motivation at the time?
Sure. So pganalyze, I started, I think, was it like 11 years ago now? So 2012 as a side project initially. And it kind of grew out of my own, I would say, frustrations with working with Postgres. So I first worked with Postgres when I co-founded a company back in 2007, back in Europe, and we were doing like social media blogging type site. And at the source of that site was a Postgres database. And so back then, there was just no good tooling to understand why our site was slow, right? Like we had essentially bad user experiences and we didn't understand why. And so a couple of years later, right, I kind of got together with somebody I had worked with at the time who, in my perspective, was a Postgres expert. And so I essentially went and said, how could we make a product out of this? How could we say, for example, one challenge at the time was, how do I know what is slow in the database, right? So I see the CPU utilization of my database, but how can I actually know what is taking time. And we could really only observe, a slow page load, but how do we actually know it is this particular query? And so what Postgres introduced around that time is an extension called PG stat statements. And what that extension does is it measures all the queries that get executed on the database side. And so the reason that's so important, right, is because you can just ask the database, give me all the queries that you've seen and how long they've taken, right? And then you can, from that, decide what to optimize, which indexes to create. And so what pganalyze essentially in its very first iteration did was literally just showing that data, right? So it was a very ugly looking bootstrap site that at the time was the way to do things. And so it was literally just pulling that data and showing it in a quick view. It didn't work as a business really in the beginning. It was more a kind of project just for our own benefit, essentially. But already that was really useful. It's just having that data of the query, which queries have run, and then also over time. So you can say, well, yesterday at 5 p.m., we saw a spike in query activity. Why was that, right? Why was it suddenly slower? And so that was really the initial focus of the product.
So I think one thing you said there is that it's the load on the database or the types and amounts of queries that are going to determine the performance in some cases. So having a slow query that you almost never run is maybe not a problem, but having millions of queries that have a performance issue is obviously a much bigger problem. So can you talk about Postgres built-in explain feature and I guess explain analyze, and what does pganalyze do that goes beyond these?
Sure. Yes. If we think back just in terms of what we talked about earlier, right, in terms of SQL being a declarative language, right, and so you're not really telling the database how to do something. And so the explain feature in Postgres, what that does is it will explain to you what the database will do, right? So generally when Postgres, gets a query, it first does the parsing of the query. It then does what's called parse analysis to actually say, well, these like tables you're referencing are actually these physical tables in the database. And then it does planning, and then it does execution. Now, the part where Postgres essentially has a lot of choice it's making is that planning process, right? Because in the planning process, Postgres will decide which indexes to use, how to join your tables, which, kind of how to group things, how to sort things, right? All these decisions are being made in the planning process. And so what the explain kind of statement does in Postgres is it will show you the query plan that is being determined in that planning phase. And what it will also show you is the cost that Postgres determines. So generally when Postgres makes a decision on which way to query a table, right, which index to use or how to join, it will do that based on a cost. And costs are essentially just units that Postgres is using. So they're not time or anything. They're literally just, this has cost 5, this has cost 10. I'll choose cost 5 because it's less cost, essentially. And so when you do just explain without analyze, really what this does is it just shows you the output of the planning stage, right? It just shows you the result of planning. The good thing about just bare explain is that it's really fast, because planning is always intended to be fast, right? Like Postgres will not spend a lot of time finding the perfect plan, because then each of your queries would be slow. Instead, what it does is it essentially does a best effort search in a lot of cases. And so explain will give you that even for very complex queries, you will quickly get the explain plan or the query plan by just putting explain in front of your SQL statement. Now, explain analyze, on the other hand, that actually runs the query. And so explain analyze is very useful if you want to know which portion of the query took which runtime. The thing to know about explain analyze, and this might be not obvious, so I'll mention it now, which is it has overhead to run explain analyze itself. And so there's some settings you can use to reduce that overhead. But one of the challenges is if you're measuring things with explain analyze, you kind of, in a sense, you're measuring a target that also is not the same as the usual execution time, right? So that there's some intricacies there. The other thing that with explain analyze that's really useful is explain analyze buffers. So buffers is a special option that you can pass when you're doing explain analyze. And the reason it's so useful is because it shows you how much data the database is loading. So you can not just see the runtime of the query and the individual parts of the query, but you can also see how many bytes of data essentially are being loaded, how many blocks of data. And so that is super useful, because ultimately a lot of times the bottlenecks in a query are I/O problems, right? And so oftentimes you end up just having slow I/O because you're going to a network storage in the cloud. And so understanding which part of your query is doing that I/O is super important. Now, what we do in pganalyze is we actually integrate with an extension called auto-explain. Now, auto-explain is really useful because instead of you running these commands interactively, right, you connecting to the database, you actually get the queries recorded by the database itself. So auto-explain says, if the threshold, for example, is, let's say 1 second, for example, Each query that is slower than 1 second will get logged to the Postgres log. Now we do, in pganalyze, we pick up those log entries. So pganalyze as a product will just parse the logs continuously and then grab these log entries that say, this query took this long and here was the execution plan. There's various settings that we recommend tuning for auto-explain so it's safe to use in production. But generally, people have reported, I would say, in the most expensive version of it, between 1% and 3% overhead, but it's definitely, close to 1% if you use the right settings. And it's just so useful because you know the exact plan that executes at the time of your query being slow, not just the plan that you see when you run a query right now.
So give us a sense of using pganalyze. Is it primarily visualizing this auto-explain? Are there completely different features that people run, say, for looking at memory or disk, or what's the basic set of options if I'm running pganalyze?
For sure, yeah, and I'll speak to, I would say, how I look at the system, right? Because we use pganalyze ourselves to optimize our own database, which I generally find is the best way to build a product is, use it yourself. And so I think first and foremost, right, it shows you data that you don't really see otherwise, right? So oftentimes today, what you would see in your cloud provider dashboard is like a very high level graph that says, this is the CPU utilization, right? Maybe you'll see something like active sessions, but you don't really see that level of detail that pganalyze shows you. And so usually when I use pganalyze, I would use our kind of query overview to see which queries are the most active. And then I would jump into an individual query. Now, for each of those queries, I can get the performance over time. Again, that is what we referenced earlier, pgstat statements. That's really data that comes from pgstat statements. Now, where I think pganalyze is unique, and I think it's even today, this is true 5 years ago, but it's still true today. What we do well is we actually link together the statistics tables, so the pgstat statements type data, and the actual Postgres log data. Right. So sometimes what's challenging is when you have these auto-explain plans, they're in your logs, but you'd have to just read through log files and it becomes very tedious. Right. And so what we do is we actually pull those up into the query page so that you see all the explain plans that were recorded for the query right in that specific query page. And so that saves you a lot of time because you don't have to go looking for log files. There's, of course, many other features that we've added to pganalyze, again, from our perspective of using it, as well as from customers kind of reporting things. One other thing I think that's noteworthy in the context of query performance is what we call query tags. So one challenge that as an application engineer that you sometimes have is SQL queries are not really what you're thinking in, right? You're thinking in ORM calls, right? Your ORM kind of abstracts the SQL query away from you. And so what we've added is a way to essentially you tag your queries with the location in which kind of the query originates, right? So you can say this line source code, this file, maybe this name of this particular controller in my application. And then the query tags feature will highlight that on the query page. And so that way I can actually understand better which part of the application is causing the slowness.
How do you think about database performance compared to general application performance or maybe operating system performance? It seems like there's a lot of similarities, but there's differences also.
Yeah, and I think in terms of tooling is maybe one way to answer this question, right? So, for example, we ourselves use a combination of pganalyze and Sentry for our own performance monitoring. So when we want to look at this from a kind of application-centric perspective, we would look first in Sentry. Now, what Sentry would show us is a trace, for example, right? So it would tell us this particular web request took this amount of time. But really that stops at the individual SQL query. And so if I'm thinking of individual users experiencing a slow web experience, I would start there and then I would go into pganalyze to really do the deep dive and really find out why the query was slow, right? Why, was this a pattern, right? Is this query always slow? I think from an operational perspective, we, for example, have our own Grafana dashboards as well. And so I think, some of the high level metrics, I think systems like Grafana or AWS CloudWatch are best suited for because they kind of give you that summary view over a lot of different pieces of infrastructure. And so to me, really, I think it's a combination, like use the right tool for the right task, right? So if you're trying to drill into your database, use something that's database specific. If you're trying to understand what, end user transactions are slow, use an APM tool. If you're trying to get a sense of your infrastructure, use something that's good for infrastructure monitoring. I think it's really good to use purpose-built tooling versus something that's generic that doesn't really do a good job.
Yeah, so it sounds like you're talking about monitoring up and down the stack kind of at all levels. How about for Postgres itself? Are there other performance monitoring or optimization tools that you use yourself?
Yeah, good question. I mean, there's a lot of projects in the open source. If you're ever interested in this, from a non-biased perspective, right? I always have my own biases, of course. There's a good list in the Postgres wiki that just lists out all the different monitoring tools. I think what I use myself, again, it kind of comes back to explain, I would say, right? So when I am looking at a slow query, what I would usually do, I would try to understand why it's slow right now. I would maybe look at a recorded explain plan in pganalyze, but then I would also, if I want to experiment, right, if I want to try out different variants of the query, like maybe I'll remove a part of the query, see if it performs differently. Usually what I would do is just run and explain on the database directly. And I think I would say that's really the most common tool that I use. Of course, there's many alternatives that people might also use for other parts. I'll give you one example. So for example, in pganalyze, we have a feature to do log monitoring, but a very popular tool to do this in the open source world without a product like pganalyze is called pgbadger. And I think pgbadger is a great tool. I've used it in the past. I no longer use it because pganalyze solves that for me. But I think there is obviously a lot of great projects in the Postgres ecosystem that are created by individuals just because they're scratching their own itch, essentially solving their own problems. So always good to find things like that.
I'll include links to these applications in the show notes. What language or languages was pganalyze written in? Is it a part of it a Postgres extension, or how does it have access to the Postgres specific data?
Yeah, it's a good question. Let me see. So I'm by trade mostly, I would say, well, I started with C++ personally, but there's no C++ in pganalyze, luckily. There's a bunch of C, which I'll get to in a moment. We started with Ruby, I think, initially. And so a lot of the web application that we have is built in Ruby. We recently started adopting Rust. So a lot of the kind of performance processing that we're doing is in Rust. So the way to think about it, right, what we're doing is you have your database server, right, and we have a component that runs on your server or close to your server in the case of managed service. And then that component sends data to our service. That data gets processed, gets stored in the Postgres database ultimately, and then that data gets queried, in our web UI. And so kind of the way our stack looks like is that component that runs in your environment, that's actually a Go application for historic reasons. Then, that sends into our statistics processing, that's Rust. And then we have a web interface that's built in Ruby. To me, it, again, comes back to using the best tool for the job, right? So I think, for example, Go, the big benefit is that a lot of cloud providers actually publish SDKs for Go. Rust, for example, I think the AWS Rust SDK is actually in pretty good shape now, but a year ago it was still experimental. And so you couldn't really access the AWS APIs in a stable way in Rust, versus Go, just works well. And so Go was a good fit there. Think of Rust, for example, in our backend, it really comes down to performance, right? So how do we make sure that we have, the least overhead essentially when we're pulling in these statistics and we're running our analysis? And so that's where kind of Rust sits. And then Ruby, I think, is just very convenient for kind of basic CRUD type applications where you're just showing data and you have like stuff like, users that sign in and things like that. Ruby and Rails is just good at that.
So is the C part you mentioned, is that an extension?
Yeah, sorry. Let me actually speak to that. So by intentionally said, we don't want to build an extension because the problem with extensions, and that is true today and hopefully will not be true at some point in the future, if you're using a managed service provider like AWS RDS, you can't actually use your custom extensions, right? So if I today went and I created a custom extension, I would have to then ask AWS to enable that extension on their system, and that is a long process, and they usually do it based on customers requesting it, not me as an individual just requesting it. And so it's very hard to get a custom extension to be adopted by the cloud providers. There's some efforts recently to improve on that, but what we've essentially said early on is we don't think that it's the right approach to build our own extension because it limits our adoption, essentially, our use. And so what we did instead, we are actually using portions of the Postgres source in our own application. So I think roughly 6 years ago, I first created a library called pgquery. And what pgquery does is it actually pulls the parser from Postgres and makes it a standalone library, right? So you can think of when Postgres gets your query, it, as mentioned earlier, it first does the parsing, then it does the parse analysis, then it does the planning, then the execution. And so that very first step of parsing is very important because when you're trying to understand what is a query even doing, right? Like which columns this is referencing, which tables is referencing, you kind of need that parse tree that first step determines. And so what pgquery does is it just plucks out that particular portion of Postgres, puts it in a C library, and then also has a Ruby wrapper around it so that what we could do with pgquery was in our Ruby application at the time, we were able to essentially just call the parser and say, this query, what is it actually doing, right? Is it an update statement? What is it updating? What's the table name? Which columns is it filtering by? So all that very in-depth analysis, we need to essentially extract the parser.
So is pganalyze today strictly a service, or is there also an open source package that you can install, or how does that work?
Yes, it's essentially a combination. So we open source parts of our libraries that we built. So pgquery being the best example of this. So pgquery is open source. If you have a use case for parsing queries yourself, you can just run pgquery in your own application. And people have done all kinds of things for that. Fun fact, if you install GitLab bundles pgquery as part of their install because they're using it in some part of their own tooling. But pganalyze as a product is a commercial product. So we are a small company. We are bootstrapped. So no VC money. It's just our own money from essentially building a product, selling it to customers. And so to make that sustainable, we've essentially chosen that parts are open source that we find are generally useful, but then the pganalyze product itself is a commercial product.
Now, before we dive into a Postgres performance specific sort of tips and tricks and just learning about it, I would like to reference 3 software engineering episodes that dealt with Postgres that are useful, you might find useful. Episode 454, Thomas Richter on Postgres as an OLAP database from 2021. Episode 362, Simon Riggs on advanced features of Postgres, 2019. And episode 328, Bruce Momgen on the Postgres Query Planner, 2018, which I found particularly interesting, the way he discussed that in detail. So one of those shows mentions OLAP. Can you talk about the difference between OLTP and OLAP, which is, I guess, the difference between transactions and analytics, particularly with respect to performance and performance monitoring?
Of course, yeah. So generally, the way I would think about it, right, is if you have your typical web application today that, let's say it's a CRM tool or something, right? That would be a typical OLTP application, right? So OLTP applications have a lot of fast queries. They're, usually a system of record type system where you're serving a web request, for example. That is a typical OLTP system. Now, an OLAP system, on the other hand, would be something more like a data warehouse, right? So where you're trying to do business analytics, business intelligence type queries, where you're trying to say, how many of my customers have done this in this time frame, and you're looking just at a lot of records, right? Now, Postgres, the good news is Postgres can do both, right? So Postgres can be used both as an OLTP system as well as an OLAP type system. Generally, though, I would say Postgres will excel at OLTP type workloads. OLAP workloads can make sense to use more purpose-built databases in some cases. Particularly, for example, one thing to note about Postgres' way of storing data is it's generally a row-based format. And so row-based formats make a lot of sense if you're querying for a small set of individual rows. But in an OLAP use case, what you're often doing is you're querying over a lot of data. And so there, a column store type format makes a lot of sense. There are actually extensions for Postgres now that do store data in columnar format. But generally speaking, I would say Postgres is very well suited for OLTP and in some cases suited for OLAP. Now, when I look at this from a performance optimization perspective, it again comes back to query plans, right? So when I optimize a query plan for an OLTP workload, I would usually have a very simple query, I imagine, in many cases, where it's more a question of how do I squeeze out that last remaining bit of performance, versus in an OLAP case, usually it's very complex queries that join a lot of data or that scan a lot of data. And so if you have the right set of indexes, you can certainly improve both, right? So indexes matter for both OLAP and OLTP. But I would say in the case of OLTP, you might be able to more purposely build an index just for the particular report you're generating once a day, for example, versus in the case of OLTP, where you have just small, fast queries all the time, you really want to look at the whole workload, right? So you really want to look at all the queries that have run in the last 7 days or last 30 days, and then get a sense for what are they querying for, right? What are they filtering for? And then optimize for that kind of set of queries versus just individual queries.
You mentioned there might be cases where you need to switch to a more specialized database. I'm guessing you've done your performance analysis and there just is no knob to turn. There's just nothing to make it faster. Is that an experience that you've had where you just don't find a solution, even though you can see the problem?
I would think about what problem you're trying to solve, right? So maybe a good analogy of this would be, if I'm analyzing data that's just stored internally and I'm just doing a report across all the data, right? So most of my reports are loading up all the information. Then, to be honest, I don't think Postgres is a good use case for that, right? If you're looking at all of your data most of the time, Postgres will be having more overhead than other systems. If you have columnar store, again, columnar stores just by design have less overhead. And even if you use the columnar extension for Postgres, that would still not be as good as a purpose-built system. However, the big benefit of Postgres would be that it integrates better with other things you have, right? So coming back to this OLTP versus OLAP comparison, what people in the last years essentially have created is the term HTAP. And so HTAP is kind of a hybrid where you have some OLTP type queries and some OLAP type queries. And so why that matters is because you're not going to choose a purpose-built database that's good at data warehousing when you're also doing, individual OLTP type queries. This was actually something back when I was at Citus Data that we saw a lot. What Citus was good at is, and why people chose Citus over other solutions, was that they had a mix of workloads. So they had a use case where they wanted to be able to do some analysis across their whole workload or across subsets of their workload, but then they also had individual users just adding records and doing inserts. And so that type of stuff is where Postgres is really good at, is combining these type of approaches. But if I had just OLAP, I would probably pick something else. Very popular these days, for example, is ClickHouse. ClickHouse is a columnar store, and that can make sense in many cases. I was referencing Sentry earlier today, just in our own tools that we use. And Sentry, for example, adopted ClickHouse for parts of their workload internally. They're also using Postgres for other parts, right? So they essentially started using both data stores because that made sense, right? It gave them the best solution to combine them.
Let's dive into indexing, probably one of the most important aspects of database performance. Just from a high level, how do you make the decision about which types to index, what type of index to make, whether to have an index? How do you decide these things?
Sure. And let's maybe, before we dive into the how to make the decision, maybe for those of you who are not familiar with all the different index types in Postgres, maybe just a quick repeat of that. So your most common index type in Postgres would be a B-tree index, right? And the way to think about a B-tree is essentially it helps you optimize filtering as well as sorting for your data. So a lot of times when your query, for example, when you have no indexes, it's maybe the best comparison. So one of the index choices is no index. And then what you're doing is you're essentially looking at a large file that stores all your data, and you're just going through it row by row, and you're filtering each row, and you're saying, does this row match the query? And if it matches, it returns. If it doesn't match, it doesn't return. And so what a B-tree index is essentially a cached data structure that optimizes that lookup so that you don't have to manually go through each row. And it does that very well, which is, I would say, 90% of cases, you should use a B-tree index. There's, of course, other index types, and we don't necessarily have to go into all the details today, but just be aware that, for example, in Postgres, when you're doing lookups like this value is included in this array, for example, you would want to use a GIN index. When you're working with geospatial data, you might want to use a GIST index or SPGIST index. In some cases, for OLTP workloads, it actually makes sense to use hash indexes. And so there's just different index types with different trade-offs that factor into your indexing decisions. Now, kind of coming back to your question of how do we reason about this, right? How do we essentially make a choice of indexes? To me, like the way I look at indexing is essentially it is the developer's job, right? So I think that maybe the first important thing to note is I don't think that indexes are the DBA's job or the DevOps job. I think it's a application engineer's job to create the right indexes. And so the way to think about that for me is you're writing your code, right? Your code makes ORM calls. These ORM calls produce SQL queries, and these SQL queries ultimately look for data in the database. Now, when you're trying to decide which index to create, really you need to be thinking about the queries you're making, right? You need to be thinking about what are those queries filtering by. So when I do a select from a table, or your ORM does a select from a table, you have a where clause, and then it says where column 1 equals something, and column B equals something else, right? Really, that is the most important piece, because this is something that the database will not do for you, right? The database will not look at these where clauses and say, oh, they're always querying for this set of where clauses, I'll create the index, right? That is a responsibility that the application engineer has. And so really it comes down to which queries are you running, what where clauses do they have that they're filtering by, and then if you want to get more advanced, which join conditions are you using and which order conditions, like how are you sorting your data? Because the best performance is going to be when you look at a combination of all the conditions you're filtering by, as well as the order in which you want your data returned, because an index can both filter the data, but it can also give you a sorted result. And you can really get tremendous performance improvements if you get this right. I can actually share a specific example that I worked with recently where we had a case where there was a 400x performance improvement, actually 414x performance improvement, where we took a query from 1.2 seconds, so roughly 1,300 milliseconds, to 3.13 milliseconds. So huge improvement. And as I referenced earlier, right, interactive page loads might be 200 seconds, right? So you could see how, before when it took 300 seconds, it was actually milliseconds, it was actually too slow, right? Somebody would have actually had a slow experience, versus that indexing change actually made a difference, and it tremendously improved that query performance to the point that was actually interactive. And that is really why I think it matters to look at the whole stack, right? Because it doesn't matter what code you're running on the application side. If you're making that single SQL query and that turns out to be that slow, right, then suddenly everything else is going to feel sluggish.
So you mentioned several different types of indexes. Is B-tree the default, or does Postgres automatically select any of these other index types in certain cases?
B-tree is the default. So B-tree is, if you don't tell Postgres which index type to use, it's just going to give you a B-tree index, which I think contributes to the fact that most people have B-tree indexes. The thing also to note there is index types relate to the operators you use in your queries. So I mentioned earlier this example, if you have column A equals some value, right? So the equals sign, that's the operator you're using in that case. Another example would be if you have a not equal sign, that would be something that your regular B-tree index cannot index well, actually. It can, I think, filter in some cases, but it doesn't work well. And there's other operators in Postgres, like your containment operator, or in JSONB, for example, you're saying, give me these JSONB documents that match certain conditions, which again, a B-tree index isn't a good fit for. And so Postgres will not make that choice for you. You actually have to tell Postgres, create index, and you say using. And by default, if you don't specify using, it's essentially assumed to be using B-tree, but you could just as well say using gin, or using gist, or using, for example, pgvector as IVF flat as a particular index type that the pgvector extension introduced. So that's a totally different index type for, vector embedding type data.
So you mentioned operators. There's something called operator classes. Does that have to do with choosing an index also?
I would argue most people listening to this hopefully don't ever have to worry about operator classes. So the quick version of it is that an operator class is essentially the behind the scenes implementation of how Postgres would match up things, right? So how Postgres would, when you have this operator in your query, how it will ultimately get back to this index type supports this operator class and then supports, this operator. So it's part of what what Postgres itself will do during planning. I think in practice, what most people will do is they will create an index, they'll run an explain on it, and then they'll realize the index isn't used, right? And so then they'll hopefully realize that part of the problem is that operator is not supported. There's actually a good overview also in the Postgres wiki. If you look at particular index types, the Postgres wiki or the Postgres documentation will actually tell you which index types support which operators. And so I think it's really more of a question of being diligent, right? When you look at your queries and you're not using an equals operator because you're doing something else, then just understand that not all indexes support all operators. It's very specific to which index type supports which operator.
Yeah, I can definitely relate to documentation having concepts which you don't actually encounter as a end user, or you may not have to deal with. You mentioned JSONB. That is a binary format for JSON that Postgres stores. Do you know anything about the history of that? It seems like when I used it, I didn't really appreciate that. It's a pretty significant addition to the database because you can store large blobs of JSON and query into that JSON. Do you know much about how that came about?
Sure, I know some of it. I think there's definitely other folks that, are the experts on it that, actually did the work here. But my understanding of the history is that, so if you recall, maybe 10 years ago, NoSQL was all the rage, right? Everybody was like, oh, stop using SQL, stop using relational databases. We'll just do MongoDB and, do lookups on JSON data. And we've obviously, come around since then, right? So NoSQL kind of died off as a concept. And these days, some people are using MongoDB, some people are using Postgres. And what JSONB really did is it brought this concept of document stores to Postgres. Now, the history here is that if you look back many Postgres versions, like Postgres 8 something, there was just a text data type, right? So if I had JSON type data, I would just use the text like data type in Postgres. I would just put it in a text column. Obviously, I could do a lookup on that text column, right? If I wanted to match the whole document, but I couldn't really query inside the document. Now, after the text type, which was always there, essentially, the JSON type got introduced, I think roughly maybe 15 years ago, I think slightly more actually, maybe 18 years ago. And so what the JSON type did is it essentially gave validation to that data type. So you actually had the fact that this was a JSON structured document, but it was still essentially text inside Postgres. Now, what JSONB is doing is very similar to what MongoDB is doing with, I think, their BSON internal representation, which is it's essentially creating, as I understand, parts of the JSON are essentially stored differently, and they're stored differently in order to enable faster lookups on the data and also to be able to index the data. So it's essentially making part of the, like, for example, the fact that you have an integer versus text value in your JSON document gets represented in a particular way, and that then enables the database to actually work efficiently on it. And what JSONB really enables for you is that you're able to do things like, let's say you have a column and you have JSON document in that column, and it's a set of key and value pairs, and you want to look up a particular key. And so in Postgres, you can essentially just say, in newer versions, you can actually use a dot syntax. In older versions, you would do an arrow, and then you would say the key name, and then it would give you that particular value that the key references. And so that is something you can index in JSONB columns, right? So you can create an index that optimizes this type of lookup. And that is enabled by having JSONB as that kind of binary structured form of JSON in the database.
So when using JSONB, is it ever necessary to pull out a key and put it in as a full class column as sort of is that faster access, or is it totally fine to just have all your data be in the JSON and query in it?
Yeah, I would definitely recommend, if you're always querying for a particular column, it's better to not have it in a JSONB, because what you're essentially doing is you're repeating all of these keys, and you're also incurring some overhead. But like lookups, they're fast, but they're not as fast as a regular column. And so if, like, usually what I see and what I think is the best practice is if you have unstructured data that is different between your different rows, right? So some customers have this data, some customers have the other ones, then JSONB is a great fit. If you always have a particular column, then I would not put it in a JSONB field. I would actually put it in a regular column, because that is going to be the best performance. It's going to have the least data storage requirements. And so essentially that mix is the best practice that I've seen.
That's kind of what I expected when I was using it. How about expression indexes? That seems like another index type, or is that an aspect of indexing?
Yeah, I would say it's an aspect of indexing. So expression indexes, one thing that's cool about Postgres has, a lot of versatility in how you can do things. And so expression indexes are essentially a way for you to index not just a single column, right? So when I do create index, I choose what to index. And so usually I would say this column or multiple columns, right? Which there's certain trade-offs on that. But let's say we're querying our users table, and we're always we're comparing an email address. And so usually what I've seen is that people want to compare email addresses lowercase, right? Because if somebody signs in with their email address typed uppercase versus lowercase, you kind of want to match it the same way. And so in your query, you would have select star from users where lower email equals a certain value. Now, what Postgres would do usually is if you had just an index on the column email, it would actually not be able to use the index, because the lookup you're doing is not on email, it is on the lower function on that email column. And so what an expression index lets you do is it lets you index that expression. And so you can actually essentially index the result of the lower function, in this case, on the email. And so your index will just have all the lowercase emails. And so that way, all the lookups are going to be fast, because you're actually going to be able to match the index to that particular query. Now, unfortunately, the inverse also doesn't work. So if you have an expression index on lower email, if you just do a regular query with just email without that function, you're not going to be able to use the expression index, right? So it's very particular to how your queries are structured, how your workload works. And you really got to understand which queries you're running to be able to make those choices, essentially, whether to use expression indexes or not.
How about pganalyze's Index Advisor? How did that feature come about, and how does it work as a developer?
Sure. And it came about as essentially this exact challenge, right? Like if I'm an engineer, I don't think about individual queries usually, right? I essentially write code, add a new feature, and then that feature has queries associated to it, but I don't really think of that day to day. And so the motivation behind Index Advisor is that your kind of feature development ultimately produces queries, and those queries ultimately run against your database. And oftentimes people don't add the right indexes because it's not something that's always part of the engineering practice. Oftentimes what happens is people do a best effort, right? They would try to understand, well, maybe this is the right index type, but they're not really looking at the whole query workload. And so the motivation behind our work on Index Advisor is that what if we took all your query workload, right, all the queries that you've run in a database, we split it up into what we call scans, which are essentially on this table, I'm filtering for this set of conditions. That's a scan for us. Across all your queries, across all these scans, we would then say, what is the right set of indexes to choose? Now, this is not a novel idea, actually. Like this idea, I think, maybe 30 years ago, there was a paper already on the problem of index selection, right? So index selection itself is generally a problem that people have encountered all the time with relational databases. I think what's unique in our approach here is that what we're actually doing, first of all, we're doing it for Postgres. So if you use SQL Server today, SQL Server has a built-in feature for index recommendations, but Postgres itself does not have anything built in. So first of all, it's in Postgres. The second thing is we are doing this across your whole workload, not across individual queries. So if you are interested in individual queries, there is, for example, the HypoPG extension in Postgres. HypoPG lets you say, if I have this query and if this hypothetical index existed, what would be the cost of the query, right? So that planning cost that we talked about earlier. And so HypoPG is a very important building block to what we're doing, but it is just a piece, right? And really what we're trying to solve is that, I would say, that mental overhead that application engineers have when they think of query workloads, right? When I'm just looking at our own database and there's like thousands of queries. And so I'm not going to go through each and every single query and look at the where clause. Like that's just way too tedious, right? It just takes too much time. And so what we essentially said, how can we do better, right? How can we actually make this be a better experience for the engineers?
I think we could spend the whole show on indexing, but there are some other topics I want to try to get to, although we probably will refer back to indices in some cases. So let's talk about queries in the sense of what performance problems can be fixed just by changing the SQL query itself. So not database configuration, not table configuration, not indices, but just more or less you wrote the SQL poorly, I guess. Do those types of situations happen?
These types of situations definitely happen. There's definitely a lot of cases that are not indexes. I just want to make one last remark on indexes, which is sometimes when you are not having an index being used, the change you should make is not add an index, but change a query, right? So sometimes it actually makes sense to rewrite the query so that you are matching your existing indexes. One example of this would be partial indexes, which just know that this is a problem. And if you if you don't see your indexes being used, just make sure you're matching your partial indexes. The one thing I would say, if we're not talking indexing, the other cases that I've seen is oftentimes one problem, for example, is regarding pagination. So one very common class of problem queries that I've observed is when you have an application, right, and you're showing a list of like results essentially in a search, and then you're not just showing the first page, but you may be showing the fifth page. And from a user perspective, usually what you would want is, a page 1, page 2, page 3, page 4, right? And you click on the fifth page and then it shows you the fifth page results. Usually how you implement this on a Postgres side is you do limit and offset. If you've ever read anything about limit and offset, then there's essentially a group of people that say offset is bad, you should not be using it. Because what Postgres will do, so let's say I'm saying, Postgres, give me the fifth page of results, right? Postgres will actually fetch all of the results and then paginate in that result set to give you that offset of, let's say each page has 100 results, right? We're giving the results between like results 400 and result 500, right? And we're giving you these 100 records. It had to also load the other records right before that. And so oftentimes, in terms of rewriting queries, the change you can make here, which unfortunately is a bit invasive, but it's a really big performance improvement, is instead of doing limit and offset, you would actually change your where clause to look up what's called key set-based pagination, where you're saying, give me all the records that are larger than this ID number or larger than this identifier. And that's going to be much faster from a query perspective, but you do have to change your query to benefit from that.
You mentioned partial indexes, and I did read about that where you could index, for example, only non-null rows was a simple case given. And I imagine it could get much more complicated than that. How about views and materialized views? Are those things that any query should consider using for performance?
So I would say views don't really give you a benefit in performance. They really give you a benefit in terms of kind of abstracting your data better, right? So if you have a lot of, like you find yourself, especially when you're running manual queries, right? So it's more actually the OLAP use case where you find yourself writing queries and you always have this really complex query that always looks the same. It always, maybe joins the same things. And you just want to have a easier way of querying. Then a view will help you do that because it abstracts essentially it's a rewrite of your query. It's a simplification of your query. It's kind of like a function call, you could say, right? So you're just kind of simplifying your query into a shorter form, and you can just say select from view, and then it will automatically translate into a much more complex query. What materialized views do, on the other hand, materialized views are a cached version of that data. So instead of the data being retrieved at query time, it actually gets stored in that form. And so the materialized view can have a performance benefit. The big downside with materialized views is that they get refreshed explicitly, not automatically. And so it's something that you have to, like you say, create materialized view on a particular query, then the materialized view will cache that data. But then the problem is if you want the up-to-date data, you do need to say refresh materialized view to get the updated version. In newer versions of Postgres, there's a version of this called refresh materialized view concurrently, which if you are on that version that supports it, definitely use that version. Usually in Postgres, concurrently means it takes less locks, so it has less overhead essentially in database. If you use the version without concurrently, it will actually block activity on that view. So if you have queries that try to query the materialized view, they will actually be blocked for that refresh. So that's just something to watch out for when you're doing a lot of refreshes.
So I'm guessing CTEs, common table expressions, are like views and that it's not directly a performance concern, but maybe they do let you write longer and longer queries. Is there any impact you've seen from CTEs on performance?
So CTEs are interesting because they're different depending on which Postgres version you're looking at. So a CTE, for those of you who are not familiar, would be essentially in an individual query. Let's say I'm joining, like I'm doing select star from my table, and then I want to join against some other data. And the other data is not just a single table, but it's maybe some other complex query that I want to run. So CTE lets you abstract that so that you could actually write with, and you say my data as, and then you have a query, a subquery that is all the data you want to work with. And then later on, you reference that CTE again in the same query. Now, in older Postgres versions, what Postgres would actually do is it would materialize the CTE. So materializing not in the sense of a materialized view, which is actually stored on disk, but just materializing in terms of storing it in memory. So that it would first run that CTE query, that subselect, remember the result of that, and then run a query like the other parts of the query against it. Now, in Postgres 12, if I recall correctly, they changed this so that instead of a CTE always being materialized, you can now either say with the name of the CTE as materialized or not materialized. So you can kind of control the behavior. Or if you don't explicitly specify it, Postgres will actually choose what to do. Now, the reason that the change was made is because oftentimes this materialization component of CTEs actually works against you because you're essentially preventing Postgres from doing certain optimizations and how it chooses its query plans. And so in newer Postgres versions, oftentimes it's actually a benefit to have that materialization not happen. But sometimes when you are trying to run your query in a certain way, you would actually want the materialization. And so then it does matter to actually add that keyword so that you are explicitly materializing and then later essentially reference just to that cached result.
Maybe I should have asked this first, but how about just join itself, the bread and butter of relational databases? What sorts of performance implications are there in how you perform a join? I'm guessing maybe it's the order, A join with B or B join with A, or what ways are there to do this better or worse?
No, you're right. So I think the most important choice, so when you're joining your tables, the most important choice that the Postgres planner has to make is which order to join the tables in. And then the second most important choice is how to join, right? Now, for the join order, there's various ways Postgres does it. I would say the most surprising thing to know is, so join order is actually quite expensive to calculate because when you try to find the optimum join order, you need to understand the costs of all the different variants. And so Postgres will actually switch over to a different way of planning if, I think by default, you have more than 10 join tables. So if you're joining more than 10 tables, Postgres will actually do something special. Be aware of that. There's certain settings that relate to that. And so once Postgres has found the join order that works. It also looks at the join method that it's using. The 3 join methods that exist are either hash joins, merge joins, or nested loop joins. You can always use a nested loop. So nested loop just means get the data for one of the tables and then iterate over each row and find the data for the other table. Because of that iteration, nested loops can be quite slow because you're essentially, if you have 2 big tables and 2 big result sets, you will have one table where you're doing a lot of small kind of queries into the table. Versus merge joins and hash joins, what they do is they load the 2 kind of results separately and then merge or hash join them together. And so that way it's much faster essentially from a just pure, lookup perspective, because it's a much simpler lookup to do.
Okay, that was some about queries. How about maintenance? Created that category, maintenance. One topic there I found was vacuuming. As an application developer, it sounds a lot like garbage collection. Is that something that your tool is able to monitor or recommend how to configure that, I guess?
So we are actually in the process of launching what we call the pganalyze vacuum advisor. And so vacuuming, for those of you who don't know, is essentially, so garbage collection is one way of looking at it. Vacuuming is essentially defragmentation, right? So the way to think about it, the way the Postgres does things, when you're doing an update statement or delete statement, the old version that you no longer need is still on disk. And so what vacuuming does is it cleans up that old version of the row. Now, some of you might ask, why don't we just remove the data right away, right? If I'm doing a delete, why do we keep that old data around? And really the answer to that is the way how Postgres determines visibility. So if you have multiple concurrent connections, it might be that another connection is still able to see that row that you're just deleting. And so that's why it's so important that Postgres doesn't just delete it right away. It actually kind of keeps it around for a bit longer until nothing else sees it. And then vacuum essentially cleans that up. Now, what I found is that vacuum in Postgres is one of those maintenance commands that are actually really, it seems really simple, but it gets really complicated. Where it gets really complicated is, so Postgres has a process called auto vacuum. And what auto vacuum does is essentially you can think of it as a more advanced version of a cron job that runs on your tables, and it will run the vacuum command on your tables on a schedule. But the schedule is not just every day at 5, but instead the schedule is when a certain condition is met, then run the vacuum. And there's a lot of different conditions. The most important one to know is that if there's a number of dead rows, right? So if you have a number of deletes, for example, or a number of updates, then at some point vacuum will kick in, auto vacuum will kick in, and will actually clean up that data and essentially make the space reusable. And so if you're seeing your table size grow and grow and grow and kind of become bloated, then oftentimes the issue is that your auto vacuum is not running often enough, and it's not actually cleaning up the data. Now, what we found is that we already collect a lot of useful data about this in pganalyze, but so far we haven't really made tuning recommendations. And so our new vacuum advisor essentially gives you tuning recommendations where it specifically says, for this table, tweak this threshold to run vacuum more frequently to avoid bloat accumulating. And we do that based on essentially looking at the data we're receiving, kind of projecting if vacuum ran more frequently, would bloat have been avoided? And then we kind of make a recommendation to change these table-specific settings.
Another maintenance task might be backups. I almost feel like some application developers these days just expect their database to be redundant and essentially never have to restore from backups. But I imagine other people still do regular backups. What are the performance implications of backups in terms of how do you not degrade the user perceived performance?
I think the good news, as you say, most people don't have to worry about backups today, right? So if you are in the cloud, I think what matters most is you understand what your company's backup policy is, right? Like how long backups should be kept, and make sure that your databases actually keep it that long. I don't really think you have to worry much about the whole database backup in that sense. What is, I think, helpful to understand is if you're doing a PG dump on your database, that is, of course, actually incurring performance. So the big difference here is what I would call a physical backup versus a logical backup. And so a logical backup would be PG dump, which actually runs queries against your database, versus a physical backup essentially reads files. And certainly, if you ran PG dump, what would happen is you would produce a slow query. It's essentially a select star on your table. And so that could have some overhead. Well, it will have overhead because you are kind of getting all the data, you're copying all the data into Postgres shared buffers, and then you're returning it to the client essentially. And so that's just slow. And so that's something that you want to watch out for if you have a large database. It's usually best practice not to do that. You might want to use a replica, right? And if have a replica that then you run PG dump on.
Okay, speaking of replica, how about just a little comment on scaling in general? So I think I mentioned this at the beginning. You have some user load and it's gotten 10 times or 100 times bigger, and your performance is suffering. And two options in most backend cases are sort of horizontal or vertical scaling. How am I going to decide which of these is going to solve my problem, or what combination of these? Because that seems like a pretty big operational question.
Yeah, and I can recall also from my experience back at Citus where we saw this problem a lot. So the way we solved this back at Citus was we essentially had this extension for Postgres, which would let you run multiple Postgres servers, and essentially you could think of your whole set of servers as one. So you could run a query, like again, for example, select star, and it could actually go across the nodes transparently behind the scenes. That is obviously the most scalable approach, right? Because you can just add more nodes. Like if you want more scalability, you just add another node. Sometimes people solve this also on the application side where they do sharding and then the application does the routing between the different nodes. So if you think of yourself as, the $1 billion company that needs to be able to scale infinitely, then certainly thinking about a multi-node approach, I think, is very useful. The one thing I would caution against there is I think there's a trend towards making everything a distributed database. And I think that is actually not a good choice sometimes. So the one thing that I recall again from with Citus, what we've done a lot of times back then, is we would actually try to make queries go to a single node as much as possible, because querying a large set of nodes for your queries is expensive. And there is some essentially speed of light constraints also in terms of making sure that things are consistent. And so what you will actually find is that some of these databases that promise infinite scalability and is all distributed, they actually end up being slower for very small, fast queries, where it's actually much better to have a single node you're querying. And so that's just something to think about is, are you doing a lot of querying across nodes? And if you are doing that, then can you partition your data in a way so that doesn't happen? There's lots of details to this, but I would still personally recommend the Citus extension. It's open source, so you can just install it in your own server. Some of my colleagues from back then are still at Azure, so they also offer a managed service for that.
How about partitioning? Is that different than replicas in terms of dividing up your data? What is partitioning, I guess, and what is the upside or downside of partitioning?
So I would say there's essentially three ways of, like if you go from a single table on a single server, right, there's three ways to scale it out. So partitioning in the simplest form can mean partitions in Postgres on a single server. So that means you do essentially have a regular table, but instead of the table being a single table on the server, it's actually multiple tables on the same server. So that oftentimes makes a lot of sense. Partitioning in that sense is useful when you're, for example, have time series data and you want to drop old partitions. That's a really fast operation. And so partitioning will help you manage large sets of data on a single server better. A variant of partitioning is what we call sharding. So sharding essentially is when you are splitting up your data, but instead of splitting it up on the same server, you are splitting it up across multiple servers. And this comes back to an extension like Citus, for example. Now, the third way of scaling out would be replication. This is something, let's imagine you have your AWS Aurora cluster. You can just add additional reader nodes. And so a reader node in Aurora is just a replica in Postgres terms. So that means it's a full copy of your database that essentially follows behind the primary that you could use for queries. The challenge there, of course, is that you're still limited to the performance of an individual node. So if your queries are really expensive, they're not going to get faster by using replicas. They're just going to spread out more. So if you have too many queries, that can be a way to kind of scale out the read workload.
Great. Well, we talked about indexing, queries, maintenance, scaling. I have one last topic to touch on, and then we'll start wrapping up. I'm not sure how much you have to say about this, but as an application developer, I'm kind of interested in the concept of stored procedures. This almost sounds to me like having your database run arbitrary code. How common are stored procedures today, and what languages can you use to write them? And can you monitor their performance? Because that starts to sound like application performance monitoring.
And I think so procedures are interesting. Like procedures could either be create procedure or create function in Postgres on the server side. What's interesting about them is I think I've usually seen them in the workloads that I see. It's a lot of times migrations from other database systems. So if you migrate from Oracle to Postgres or SQL Server to Postgres, that's where I see a lot of people, like a lot of old school databases, so to say, use procedures to encode business logic on the database. And it kind of has grown out of fashion since then, I think, right? So if you looked at applications written in the last 10 years, most of the time people don't do that same level of putting business logic in a database. I think part of it has to do with just, the functions on a database site being more constrained in terms of which languages you can use, but also harder to debug. Now, there is a trend actually where that's changing a bit. So most recently, there was an extension release called PL Rust. And PL stands for programming or procedural language. And so Postgres actually has a system that's extendable for using different languages. And so, for example, if you want to write JavaScript in your Postgres, there's PL V8, which is the V8 JavaScript engine. If you want to run Python in your Postgres, there's PL Python. And more recently, there's PL Rust. Now, what's notable about PL Rust is that it's a community project that, essentially the focus around the pgrx extension framework started, which lets you write C-level extensions, essentially, but in Rust. Now, PL Rust is a trusted language, or aims to provide a trusted language. What trusted languages mean is that it's really meant for application code that runs in the database versus you extending the database server. And so what's really nice about PL Rust is that specifically Amazon RDS also added support for that recently. So if you are in RDS, you can actually now deploy your Rust functions to your RDS database as well using PL Rust. Now, if we think about how we want to debug the performance of that, that's where it gets a bit tricky. So there are ways to track function performance on Postgres. So they will show up as a query, right? So just the fact that, query runs will show up. And then each function will also kind of, when it runs queries itself inside the function, these queries will also be visible in tools like pgstat statements. And through that will also be visible in pganalyze, for example. But where it gets tricky is when you have very complex functions. Oftentimes the tooling today is a bit lacking, and the tooling really on the Postgres side, unfortunately, to reference back which part of the function caused which query to be slow. And so it actually becomes a bit harder to debug. And so I personally don't do a lot of putting logic into functions that do a lot of stuff on the database side, just because of that extra level of indirection, making it harder to reason about, harder to profile. And so that's kind of, I would say use with caution, but if you have a workload where this makes sense, there is definitely good options today to do it.
I was kind of relieved when you said it's potentially going out of style. It sounds like super powerful, but also potentially very hard to manage in terms of your application logic being split and partially on the database.
Yep, that's exactly right.
So let's start wrapping up. What's next for pganalyze? Say what features are coming this year, or community events, or just what are you looking forward to in pganalyze? And then we'll talk about Postgres.
For sure. Yeah. So I think for us at pganalyze, it's really more about how can we make Postgres smarter? How can we make Postgres work better for you, right, as an application engineer? So we are about to launch our new vacuum advisor, which will, kind of give you the right per table tuning insights. We just gave a talk at PGCon in Ottawa, which was finally an in-person conference again after many years. And so there we talked about our new index selection algorithm. And so we're going to release a new version of Index Advisor later this year that features that new constraint programming-based model for Index Advisor. And then generally, I think the way we're looking at this is how can we give you the right data at the right time, right? So ideally, how can we notify you and alert you of a problem in your database proactively that really ties to specific queries or ties to specific indexes or tables, for example?
Yeah, just as an aside, I think one of your features was notifying you about a problem before it gets bad. So there is a dashboard that you can set up alarms with and just kind of keep an eye on things.
That's right. Yeah. And one practice that I've seen, especially larger companies where you have, data platform teams adopt, is that they've actually adopted pganalyze as a way to get Slack notifications. So we'll actually put, here's a new missing index, and we'll put that in your Slack channel for your individual application teams, which is really useful just to, take a little bit of a burden off of that central data team that today has a lot of the manual work here. So it's just a question of getting the data to the right people in the right channel.
How about Postgres itself? Is there any major releases coming up, particularly related to performance, or just any features you're looking forward to there?
Yeah, so Postgres is on generally a yearly release cadence. And so we'll have the Postgres 16 release that's currently in beta. Will probably come out in September or October. That's the usual schedule. Depends a bit on the release candidates and if there's any major bugs found. And Postgres 17 development has started now. The branch just opened about a month ago. And so what's really exciting for me, I think in 16, from a performance optimization perspective, there's a new way of getting statistics about the I/O kind of performance of the system. So there's a view called pgstat I/O that Melanie Plageman kind of contributed to Postgres. And what that new view really does is it lets you say which part of the system is creating I/O. right? So it lets you say, well, is it the vacuuming? Is it the queries? Is it something else that's causing things to be slow? And so you kind of have this high level, kind of bird's eye view on the whole database activity that you didn't really have before. And again, it's coming out in Postgres 16. And I think we'll extend pganalyze to read that view and kind of provide insights based on that as well. In Postgres 17, which is currently under development, I'm really excited about asynchronous I/O. There's a lot of work ongoing behind the scenes about asynchronous I/O and how it makes the database faster. We'll see how much actually, gets into Postgres 17. So there's always, a bit of ambiguity early in the development cycle. But I think what Andres Freund and Thomas Munro and team have worked on there's some really interesting kind of patches being worked on for Postgres.
Great. Where can people read more about you and pganalyze and even Postgres? I'm curious if there's any niches in the community you can point to that are interesting to follow. I know it's such a big project, might be a little intimidating to people. Just curious how you found the community and what resources you like to use.
For sure. So let's start with Postgres. So I think what I read, which I would, if you're really into it, what I would encourage you reading is the Postgres Hackers mailing list. So the Hackers mailing list is it's like the Linux kernel mailing list or the LLVM project mailing list. So it's very technical, a lot of deeply technical content, but that's where all the development for Postgres happens, right? So Postgres is a community project. It's not a single company behind it. It's many people contributing. And so you will see each and every decision being made out in the open, essentially. And so that's really fascinating to observe and just to read the mailing list. And again, that's PG-SQL Hackers, which you can find on the Postgres kind of project mailing list. Otherwise, I would say, we at pganalyze, for example, if you're interested in just, what's new with Postgres, we actually record a weekly series called 5 Minutes of Postgres, where I'm essentially featuring what's new with Postgres. So if you just want to keep up with Postgres things, you can subscribe to 5 Minutes of Postgres on YouTube. And then if you're interested in pganalyze, we have a newsletter that we send out each month. I, for example, have a Mastodon account. We have a Twitter account for pganalyze. So if you want to follow us on social media sites, that's, of course, an option as well. And in general, feel free to email us anytime. We generally try to be approachable and answer any questions you have about what we're doing or what we're talking about.
Excellent. And I'll put links to all those in the show notes. Thanks, Lukas, for your time today.
Of course. Thank you, Philip.
This is Philip Winston for Software Engineering Radio.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.